So, what's your name? What's your title and where do you work?
Hi, my name is Elise Rumpf, and I'm a research geologist with the U.S. Geological Survey at the Astrogeology Science Center.
My name is Greg Vaughn. I'm a research scientist with the U.S. Geological Survey Astrogeology Science Center here in Flagstaff.
The Astrogeology Science Center is really unique. It's the only USGS office that looks at other planets. So a lot of what we do is studying the geology of other planets. The term astrogeology is actually a combination of the word astronaut and geology. We were founded in the 60s to train the Apollo astronauts about how to interpret geology when they went to the moon. We also created the first maps of the moon, of the lunar surface, from some of the first satellites that went around the moon, and from the data that the astronauts brought back from the moon.
The Planets Project is a collaborative partnership between curriculum development experts and educational professional development experts and subject matter experts and teacher networks across the country. And our team in the Astrogeology Science Center serve as subject matter experts. We help write some of the content and we review the content for scientific accuracy. PLANETS is an acronym. It stands for Planetary Learning that advances the nexus of engineering, technology, and science.
What is your role on Planets?
Well, at the USGS, I'm the project manager over there. And we have several people over there who work on the Planets project, and we are primarily subject matter experts, or SMEs. And what that means is that we help write the curriculum. We also review all the curriculum to make sure that all the information in there is correct, so that the things that we're going to teach students through our curriculum is all correct and perfect.
What is your role at the USGS other than Planets?
Well, I consider myself a planetary volcanologist. So that means I study the physics of volcanoes, mostly lava flows, so how lava flows move, how they interact with the ground beneath them. And I look at lava flows on Earth and on the Moon, on Venus, on Mars, and because they're all really similar. So one of the main things I do is terrestrial analog studies. So what that means is I go into the field here on Earth and I look at the lava flows and I try to, determine different characteristics of the lava flows or how they were emplaced, and then we can compare that to lava flows on other planets to try to figure out how they were emplaced or the history of the volcanoes there. There's actually a lot of volcanics on other planets. Most of it's really old, most of it's millions or billions of years old, but we do know that there's active volcanism on Io, and we think probably active volcanism on Venus.
Wow, that's cool. So Io is a moon of Jupiter?
Yes, Io is a moon of Jupiter.
How many moons are there in the solar system?
We're not totally sure yet. Right now, there are 194 moons that we know of. So the term moon is interesting. Technically, we would call it a natural satellite. So the Earth has one moon, we call it the moon. But a lot of other planets have a lot of moons. So Jupiter and Saturn both have about 80 moons. So out of the 194 moons that we know of so far in the solar system, most of them are around Jupiter and Saturn.
So you helped develop the Water in the Solar System Science Series, correct?
Yes.
What is the Water in the Solar System Science Series all about?
Okay, the Water in the Solar System Science Series was designed to complement the Testing the Waters engineering unit to provide a little more scientific content and go into some more detail about water throughout the solar system. The first activity focuses on something we're all familiar with, water on Earth. Where is all the water on Earth? It's located in various different reservoirs, the atmosphere, it's on the surface, it's also in the subsurface, underground. And turns out, one of the takeaways from that activity is that even though the Earth has a lot of water on it, a lot of it is not very easily accessible and a lot of it is not usable because it's too salty, like the oceans. And the second unit is focused on water throughout the solar system. We all think of Earth as a water planet because water is very visible on Earth. But as it turns out, there's a lot more water in the solar system that's located elsewhere than here on Earth. And most of it is located out in the outer solar system in the moons of Jupiter and Saturn. Although it's mostly frozen, it's there. And water is fairly ubiquitous throughout the solar system. From Mercury out to beyond Pluto, we find water almost everywhere we look. And so that was the focus of that was one of the important takeaways of the second activity.
So this unit is about water in the solar system. So why water? Why did you decide to focus on water?
Well, one of NASA's primary missions is to look for life in the solar system. And as we know, life on Earth really depends on water. And so when we're looking for life on other planets, the first step to doing that is to look for where there's water.
Cool. So is there water on other planets and moons in our solar system?
Yeah, it turns out there's a lot of water on other planets and moons. A while back, we weren't sure, even a few decades ago, we didn't think that there was water on Mars, but it turns out there's a lot of water on other planets and other moons. And it's really important to find that water. For one, if we were looking for life, we definitely want to start with a place that has water, but also it's a really great resource. So as humans, if we're going to continue to explore the solar system, we want to go places where there is water, because it's really expensive to take water into space. Because of our rocketry, every ounce of weight that you take up with you costs more money and more fuel, and it's really difficult to take it up there. So if we know that we're going someplace with water and we can use that water, that's a really good resource for us, because then we can bring less water with us.
I've heard that you can also use water as fuel. Is that true?
Yeah, it's true. There are ways to use water as fuel. And this is important because if we go to a planet or a moon and there's water there, we don't have to bring as much fuel to get back. So we can extract the water from the surface of the planet or moon that we're on, and we can use that as fuel to get back. We can also use it as fuel while we're there, so to power the scientific systems and the life systems to keep the astronauts alive while we're there.
Awesome. Sounds like water is really important for space exploration.
Yeah, water's super important.
So how did you decide to represent the amount of water on each planetary body for this activity?
With all the objects in the solar system, there's a huge range in the amount of water that's present. Some bodies in the solar system, like Jupiter's moon Io, have essentially no water. And at the other end of the spectrum, Jupiter's moon Ganymede has a huge amount of water, more than 50 billion cubic kilometers of water. Again, it's just a big ball of ice out there. One of the challenges for creating a deck of cards was to represent the amount of water on various different bodies throughout the solar system accurately, but also using a simple 1 or 2 or 3 digit integer that's inside a little water droplet icon on the cards. If you consider the amount of water that's on different planetary bodies, if you take all that water off, if you suck all that water off of a planetary body and put it in a big ball or a big sphere, you can represent that volume by a simple number, which is the radius of that sphere.
Okay, let's get into the weeds here. How did you use math to get from the actual volume of water on each planetary body with up to 10 orders of magnitude down to these little water drop values on the cards with only 3 orders of magnitude?
So how do we accurately represent the amount of water estimated to be in various reservoirs on different planetary bodies using a single number inside a little water droplet icon? We wanted to get it right. We want it to be as accurate as possible. So the volume of water that's estimated to be present on the various planetary bodies in the solar system spans from 0 to about 50 billion cubic kilometers. For example, Jupiter's moon Io has essentially no water on it. On the other hand, Jupiter's moon Ganymede has the most water of any object in the solar system. It has about 50 billion cubic kilometers of water. Now that's a 10 order of magnitude difference. And we can't represent that much variation with a small number inside a little water droplet icon on a playing card. So clearly the scale we use cannot be linear. So the first non-linear operation we did was to represent volume as the radius of a sphere. Now the formula for the volume of a sphere is volume is equal to 4/3 times pi times the radius cubed. Representing volumes using the radius of a sphere reduces the variance to about 4 orders of magnitude. So we're getting closer, but we're not there yet. It turns out if you plot all of the bodies in the solar system in increasing order of how much water they have and fit a curve to those data, it turns out that curve can be represented by a mathematical formula, a power law function. And if you solve for one of the variables, x, in this power law function, you can represent the amount of water in each reservoir on each planetary body in a little as a 1, 2, or 3 digit number inside these water droplet values. The final result is that every number in the water droplet on the back of these cards is mathematically relatable to our current best estimates for how much water is in each reservoir on each planetary body throughout the solar system. One of the cool things about it is that you can look at this card, this planetary information card, and look at the water droplet number on the back, and you can back calculate.
So why did you decide to do a card game to learn about water in the solar system?
It is a very effective and fun way to present a lot of information. You can play games with these cards, and we came up with a lot of different types of games you could play. And you end up learning about the distribution of water throughout the solar system without even really realizing you're learning.